Hello, Accelerated Chemistry students. This is Ms. Crisafulli, and this is your Chapter 3, Section 1, video notes all over using and expressing measurements. So let's first talk about scientific notation. A measurement is a quantity that has both a number and a unit. So in chemistry, you're often going to encounter very large or very small numbers. So you can work more easily with very large numbers or very small numbers by writing them in what we call scientific notation. So scientific notation is, like I said, a way to represent large or small numbers. So for example, the mass of the hydrogen atom is all of those zeros and then 167 grams. And 2 grams of hydrogen contains all of those atoms or molecules. So scientific notation is a way that we can represent that small mass of a hydrogen and the large amount of molecules in hydrogen more efficiently. So scientific notation is the product of two numbers, a coefficient and a 10 raised to a power. So the coefficient is the number that's written first, and it's always a number between 1 and 9. So for example, 1.67 times 10 to the minus 24th grams, that is written in scientific notation. The coefficient, which is out front at 1.67, is a number that's between 1 and 9. And we have 10 raised to a power, and it's raised to the negative 24th power in that example. And also, 2 grams of hydrogen is composed of 6.02 times 10 to the 23rd molecules. Again, 6.02 is our coefficient, and 6.02 is a number that is in between 1 and 9, and 10 to the 23rd is a 10 raised to a power, and it's raised to the power of the positive 23rd. So how do we convert from expanded form into scientific notation? Expanded form is going to be when you have all of the zeros either before your numbers or after your numbers. So for numbers that are greater than 1, you're going to move the decimal to the left until there is 1 digit to its left. And then the number of places you moved is going to be equal to your exponent number. So let's look at an example. So 45,450 grams. So our decimal for this number is technically after the 0. So we're going to move that decimal point once, twice, 3, 4 times. And when we move the decimal 4 times, that means that our power of 10 is going to be raised to the 4th power. So this in scientific notation would be 4.5450 times 10 to the 4th grams. Now, what about if you have numbers that are less than 1? So then you're going to move the decimal to the right, stopping after the first non-zero number. So the number of places that you move to, the decimal point again is going to be your exponent number. So let's look at an example. So 0.00453 milliliters. So we're going to move the decimal point once, twice, 3 times. So our answer is going to be 4.53 times 10 to the minus 3rd. Now remember, this is minus 3rd because this number is technically less than 1. So when you move the decimal point, the number of times indicated by the exponent. That's how you go from scientific notation to expanded notation. So you're going to move to the right if your exponent is positive, and then you're going to move to the left if your exponent is negative. So let's look at an example. So 8.07 times 10 to the 2nd. So it's times 10 to a positive 2, which means that we're going to move our decimal point to the right. So that means that we're going to move this decimal point once, twice. So our number in expanded notation is going to be 807. Now, what if our example is the following, 1.2 times 10 to the minus 4th. So we're looking at that exponent again. That exponent is a negative number, so that means we're going to move our decimal point to the left, and we're going to move it to the left 4 places. So once, twice, 3, 4 times. So that means that we're going to have to put 3 zeros in front of our number. So our number is going to be 0.00012. And that's how we go from expanded notation to scientific notation and from scientific notation to expanded notation. So now let's talk about mental math and scientific notation. Now, I know you're going to be allowed to use a calculator on some of your problems for me, but I want you to be confident. You are bright young men and women, and you can do this math in your head. So let's talk about multiplication and division. So when you multiply or dividing and you have scientific notation, you're going to multiply or divide the base numbers. That's going to be your coefficients. And then when you're multiplying, you're going to add the exponents. And when you're dividing, you're going to subtract the exponents. So let's look at multiplication, an example. So if we have 3 times 10 to the 4th times 2 times 10 squared, what is that going to be equal to? Well, the first thing you're going to want to do is you're going to want to do exactly what we said. So a multiplication, you're going to multiply your base values together. So that's the 3 times the 2. And then you are going to add the exponents that are for the powers of 10. So that's going to be 4 plus 2. And when we do this math, 3 times 2 is 6, and 4 plus 2 is 6. So this answer is going to be 6 times 10 to the 6th. Let's look at another example. If we have 2.1 times 10 to the 3rd times 4.0 times 10 to the minus 7th, how are we going to solve this? So let's rewrite this. So we're going to have 2.1 times 2.1 times 4.0. And then that's going to be multiplied by 10 raised to the 3 plus the negative 7. So that answer is going to be 8.4 times 10 to the minus 4th. It's not as hard as you think it is. You just have to take it step by step. Now let's look at a division example. So we're going to take 3.0 times 10 to the 5th divided by 6.0 times 10 squared. So we're going to rewrite this so that we have 3.0 divided by 6.0. So we're going to do that division first. And remember, when you divide, you subtract your exponents. So our answer here is going to be 0.5 times 10 to the 3rd. And since we want to write it in scientific notation, 0 is not a digit between 1 and 9. So we're going to move our decimal point 1 place to the right, which means that the better representation of this answer is going to be 5.0 times 10 squared. Now, what about when we're doing addition and subtraction? So the exponents must be the same when you're adding and subtracting numbers. So what you're going to do is you're going to change your numbers to make this possible. So you might have to move decimals around so that the times 10 to a power for your two things that you're either adding or subtracting, they need to be raised to the same power. So they both have to be 10 squared, or they both have to be 10 raised to a power of 3. So when you add or subtract base numbers, you do not change the exponent. This is different than the multiplication and division. So remember, if the decimal move makes the base number smaller, the exponent is going to increase. And the same is true for the opposite. If the decimal makes the base number larger, the exponent is going to decrease. So let's look at an addition subtraction example. So we have 5.4 times 10 to the 3rd plus 8.0 times 10 to the squared. And we want to add these two values together. Well, 10 to the 3rd and 10 squared are not the same exponent, so we can't add them together as is. So what we need to do is we're going to need to change one of these. So we're going to change the second one to both have times 10 to the 3rd power. So we're going to move that decimal point 1 place to the left and make it 0.80 times 10 to the 3rd. Now what we can do is we can add our base numbers 5.4 and 0.80, and then our answer will be times 10 to the 3rd. So we're going to add those together, and we get 6.2 times 10 to the 3rd. And it's as simple as that. So now let's talk about how to use it using a calculator. So for example, if we have these two quantities, 5.44 times 10 to the 7th grams divided by 8.10 times 10 to the 4th moles, and we want to type this into our calculator instead of doing mental math, how would we do that? Well, it depends on what kind of calculator you have. For my class, you are needed to either have a TI-83, 84, or a TI-30, which is basically a simple scientific calculator. So first thing you're going to do is you're going to type in 5.44, and then you're going to either hit EXP, EE, or second, and then comma, depending on what your calculator is. And then you're going to type in 7. So what this EXP, EE, and second comma do is they put in your calculator times 10. And then you have to tell your calculator to what power is that 10 being raised. So then what you're going to do is you're going to hit divide, and then you're going to type in the second part. So it'll be 8.10, either EXP, EE, or second comma, depending on what calculator you have. And then tell it again what power it is, times 10 to the 4th. And then you're going to hit equals. And if you type all of this in correctly, you should get 671.60493. And I'm going to round that to 672 grams per mole. Or if we were going to write it in scientific notation, we would write 6.72 times 10 squared grams per mole. So we've talked about scientific notation, how to go from expanded notation to scientific notation, and to go from scientific notation to expanded notation, how to multiply, add, and subtract them both using a calculator and using some mental math. But now let's talk about accuracy and precision. So accuracy by definition is how close a measurement is to the accepted or true value. And precision is how close a series of measurements are to each other. So to evaluate the accuracy of a measurement, the measured value must be compared to the correct value. To evaluate the precision of the measurement, you must compare the values of 2 or more repeated measurements. So let's look at this example of comparing accuracy and precision. So if we were to look at these dartboards, the first dartboard on the left is precise because all of those shots are close together, but it's not accurate because remember, when you're trying to hit a dartboard, what is your goal? Your goal is to hit the bullseye. That is the correct answer or the accurate answer. So that shot in the first dartboard, those shots are precise, but they're not accurate. Now the second dartboard, those shots are not precise because they're not close together, but they are accurate because they are closer to the bullseye. The third dartboard, they're neither precise nor accurate because they're not close to the bullseye, nor are they close to each other. And then the final dartboard, those shots are both precise and accurate because all those shots are around the same section of the dartboard, and they all hit the target, which is the bullseye. So there's a difference between the accepted value, which is the correct value for the measurement based on reliable references, and the experimental value, which is the value measured in a lab. And that's how we determine error. So the difference between the experimental value and the accepted value is called error. And there's an equation for it. Error is equal to the experimental value minus the accepted value. Now, error can be either a positive or negative number depending on whether or not the experimental value is greater than or less than the accepted value. So sometimes it is useful to calculate the percent error. And the percent error is a measurement that is the absolute value of the error divided by the accepted value multiplied by 100. What is that? Well, don't worry. I have an equation for you. So the equation looks like this. The percent error is the absolute value of the error divided by the accepted value times 100. So let's look at a sample problem. So let's calculate percent error. So the boiling point of pure water is measured to be 99.1 degrees Celsius. Calculate the percent error. This is a 3-step problem because we are going to be doing a numerical problem. So we have to think about this in 3 steps. So we're going to analyze first, calculate, and then evaluate our answer to make sure it makes sense. So let's look at analyze. So we're going to list the knowns and unknowns. So we know that the accepted value of boiling point of pure water is 100 degrees Celsius. And then we're going to use the equation for percent error to solve the problem. So our knowns are experimental value, which was 99.1 degrees Celsius, the accepted value, which is 100.0 degrees Celsius, and our unknowns are the percent error. So we are going to calculate. So we're going to start with the equation for percent error. Remember, percent error is equal to the absolute value of error divided by the accepted value times 100. And how do we get that error again? So the first thing we're going to do is we're going to solve for error. So remember, error is the experimental value minus the accepted value over the accepted value times 100. If you want to write this equation down instead of error over accepted value, that's okay. This plugs both of them in together. It makes it a little bit simpler for you. So if we were going to do this, this is what this would look like. The absolute value of 99.1 degrees Celsius minus 100.0 degrees Celsius divided by 100.0 degrees Celsius times 100. So when we do this, we do the subtraction on the top and we end up with 0.9 degrees Celsius, and we're going to divide it by 100 degrees Celsius. Celsius cancels because if the unit's in the numerator and the denominator of an equation, that can cancel. So our final answer will be 0.9%. So now let's evaluate. Does this make sense? So the experimental value was off by about 1 or 1/100th of the accepted value. So the answer does make sense because 0.9 is about 1. So now let's talk about significant figures. Significant figures in a measurement include all the digits that are known plus the last estimated digit. So if I were to measure this paper clip at the bottom, I would line up so that the 0 is at the edge of the paper clip, and I would read. This would be read 2. We know for sure that it is more than 2, and then we know for sure it is more than 3. And so the next estimated digit out is the 8. So it's 2.38 centimeters long is the size of this paper clip. So let's look at this example. So we know for sure that that arrow is more than 2 but less than 3. And then we also know for sure that that arrow is at a place that is more than 2.8 but less than 2.9. So now this ruler allows us to estimate the length of where that arrow is, or the spot of where that arrow is, to about 2.85 centimeters. And that shows that this measuring device is 0.01 in the preciseness of its measurements. So if we were to look at these 3 examples, the first one is the highest place that it's marked to, is the tens place. So you can read it to the ones place. So that means that that dashed line in the first up top, you know that it's above 60, but less than 70. So you can estimate that it's about 67 centimeters in length. The next one, that device is marked to the tens place. So you need to read out one more place, which is the hundredths place. And so this measuring device reads that it is more than 0.4, but less than 0.5. And so we need to estimate out the next digit would be 8. So it's about 0.48 centimeters long. And then the last device that we're looking at, if we were to measure the length of that, we can see that that dashed line is longer than 6, but less than 7. And so we can estimate out the next digit. So it'll be 6.2 centimeters in length. This is going to be more easy for you once we have more practice, and we'll have tons of practices in the lab over tomorrow in class. So measurements must always be reported to the correct number of significant figures because calculated answers are often dependent on the number of significant figures in the values used in the calculations. So let's talk about the rules for calculating significant figures. So every non-zero digit in a reported measurement is significant. Zeros appearing between non-zero digits are significant. So what does that look like? That 0 is in between 4 and 1. So that number, 4012, has 4 significant digits. The 4, the 0, the 1, and the 2 are all significant. The leftmost zeros appearing in front of non-zero digits are not significant. What does that mean? Well, if we look at this, that 0 in front of that decimal point, remember the number reads 0.421, that 0 in front of that decimal point does not count because it's in front of the 4, which is a significant digit. So this answer only has 3 significant digits to it. Zeros at the end of a number and to the right of a decimal point are always significant. So if we were to look at this answer, this example, 1.010, that has 4 significant figures because the 1.010, that 0 in between the two ones is a 0 that is significant because it's captured between the two ones. And the 0 on the end is at the end of the number, and it's to the right of a decimal point, so that's significant as well. Now, zeros are at the rightmost end of the measurement that lie to the left of an understood decimal point are not significant if they serve as placeholders to show the magnitude of a number. Oh my goodness, what does that mean? So let's look at this. So 7,000 meters, that has 1 significant figure. There are no decimal points, and those zeros at the end are just placeholders. So they are not significant. They show you how big the number is. And then there are unlimited number of significant figures if the number is counted exactly or has a definite quantity. So the fact that we have 28 people in our class, or that there's 60 seconds in 1 minute, those are definite, defined quantities, so they have an unlimited number of significant figures. So how to count significant figures. So you're going to start counting from left to right at the first non-zero number. So if there are zeros at the beginning of the number, you're not going to count them. And if the decimal point is present, then you're going to count any rightmost zeros. Those are the tricks. So if a decimal is not present, then you don't count the rightmost zeros. All of these are tricks, and we're going to go through some practice problems. So let's look at sample problem 3.3. So counting significant figures and measurements. So how many significant figures are in each of these measurements? 123 meters, 4,506 millimeters, 9.8000 times 10 to the 4th meters, 22 meter sticks, 0.07080 meters, and 98,000 meters. And this is a 2-step problem because it's a non-numeric problem. So we're going to analyze each one of these, and then we're going to solve them. So let's start. So we're going to locate each zero in the measurement and determine if there's a decimal point, which values and which rules are going to help us to determine which of these are significant digits or not. So let's solve this problem. So we're going to apply the rules for determining significant figures, those 6 rules that we used, and then we're going to answer these. So let's look at the first one, 123 meters. Well, all of those values are non-zero digits, so they are all going to be significant. So the first one has 3 significant figures because of rule 1. Let's look at the second one. The second one has 5 significant digits because both of those zeros are in between non-zero digits, and that's rule 2. The next one, 9.8000 times 10 to the 4th, has 5 significant figures because of rule 4. There's a decimal point, and so all these zeros to the right of that decimal point are significant. 22 meter sticks has unlimited significant figures because of rule 6. It's a definite quantity. 0.07080 has 4 significant figures in it. Those 2 zeros in the front, the 0.0, do not count because they are in front of a non-zero digit. And then the last one only has 2 significant figures because there's no decimal point, and the 000 at the end make the number 98,000. So they're just placeholders like rule 5 states. So let's talk about sig figs and calculations. A calculated answer cannot be more precise than the least precise measurement from which it was calculated. So the calculated value must be rounded to make it consistent with the measurements from which it was calculated. So to round a number, you must first decide how many significant figures the answer should have. And then once you know the number of significant figures your answer should have, you're going to round to that many digits counting from the left. So if the digit immediately to the right of the last significant digit is less than 5, you're going to drop that value, and the value of the last significant digit is going to stay the same. If the digit in the question is 5 or greater, the value of the digit in the last significant place is going to be increased by 1. Basically, what does that mean? If you have a number and the last significant digit, the number to the right of it is less than 5, you're going to round down. And if it is greater than 5, you're going to round up. regular rounding rules that you are used to. So let's look at a sample problem. So we're going to round these measurements. So round off each measurement to the number of significant figures shown in parentheses. Write the answers in scientific notation. So 314.721 meters, we're going to round that to 4 significant figures. And then 0.001775 meters, we're going to round that to 2 significant figures. And then 8,792 meters, we're going to round that to 2 significant figures. So let's do each one of these one at a time. This is a non-numeric problem. We're just doing some problem solving. So this is going to be a 2-step problem. So first, let's analyze. So we're going to use the rules for determining significant figures and round the number in each measurement. Then apply the rules for expressing numbers in scientific notation. So let's look at the first example. So we're going to start from the left and count the first 4 digits that are significant. So if we were to do this, 3, 1, 4, and 7 are all significant because we need to round this number to 4 significant figures. Now, this 2 is less than 5, so we're not going to round up. So we're going to round this to 314.7 meters. That is rounded to 4 significant figures. And then we're going to write it in scientific notation. So if we were to write this in scientific notation, that decimal point needs to get moved 2 places to the left, which means that our number is now going to be 3.147 times 10 squared meters. Let's look at the next problem. So we're going to start from the left and count the first 2 digits that are significant. So we're going to skip all the zeros in the front. And so 1 and 7 are significant. Now that 7 is greater than 5, so we're going to round up. So that means that this value is going to be 0.0018 meters, and we're going to change that into scientific notation. So it's going to read 1.8 times 10 to the minus third meters. Remember, this has a negative exponent in scientific notation because this value is less than 1 when we have it in expanded notation. Now let's look at the last problem. We're going to start from the left and we're going to count to 2 digits that are significant again. So our number was 8,792 meters and we need to round it to 2 significant figures. So 8 and 7 are significant. 9 obviously is greater than 5, so we're going to round up. So this is going to end up being 8,800 meters. And if we were to write that in scientific notation, it would be 8.8 times 10 to the third meters. So that's how you round our numbers. So now let's talk about rounding sig figs in scientific calculations. So let's talk about addition and subtraction first. The answer to an addition or subtraction calculation should be rounded to the same number of decimal places, not digits, as the measurement with the least number of decimal places. So let's do an example. So let's look at the following 2 examples. So 12.52 meters plus 349.0 meters plus 8.24 meters is the first problem, and then 74.626 meters minus 28.34 meters. We're going to do these 2 and we're going to round them correctly. And this is a 2-step problem, so we are going to analyze this and also solve. So let's first analyze. So we're going to perform the specific math operation, then round the answers to match the measurement with the least number of decimal places. So let's align the decimal points and add the numbers. So I am going to align all of our decimal points so they line up very nice. So we have 12.52 meters. Then we have 349.0 meters. Then we have 8.24 meters. So all of our decimal points are lined up, and I'm going to add those values together, and we get 369.76 meters. Now, I'm drawing a red line to show where our last decimal place is. That 0 is our last decimal place. So that means that we need to round this number to the tens place. So that 0.7 is going to be our last digit. The digit to the right, 6, is greater than 5, so we're going to round the 7 up to 8. So our final answer and the correct number of significant figures for this addition problem is 369.8 meters. Now, Ms. Crisafulli, this is very particular. Yes, because I will mark answers wrong if you do not round them properly. So let's look at the second one. Remember, this is going to be subtraction. So again, we're going to align our decimals. So I aligned our decimals, and I'm going to do the math. So now the hundredths place is the last digit, so that's going to be where we're going to round to. And so 6 is bigger than 5, so our answer needs to be rounded up, so 46.29 meters. So now let's talk about multiplication and division. Multiplication and division, you need to round your answer to the same number of significant figures as the measurement with the least number of significant figures. So the position of the decimal point is not going to have anything to do with the rounding process when you're multiplying or dividing. So let's look at an example. So we are going to do the multiplication and division for these 3 problems, and then we are going to round our answers to the correct number of significant figures. So this is also a 2-step problem. So first, we are going to perform the specified math operation and then round to match the answer with the least number of significant figures. So let's look at the first one. So 7.55 meters times 0.34 meters. So 7.55 meters has 3 significant figures. 0.34 has 2 significant figures. So let's do the math first. When we do this calculation, we get 2.567 meters squared. Remember, a meter times a meter is a meter squared. Now, the 2 numbers that we multiplied together, 0.34 had 2 significant figures in it. So that means that we need to round our answer to 2 significant figures. So that means that 2.567 is going to be rounded to 2.6 meters squared. All right, let's look at another one. So 2.1 meters times 0.70 meters. So again, 2.10 meters has 3 significant figures in it. 0.70 meters has 2 significant figures in it. Let's do the math. So we get 1.47 meters squared. And again, our answer needs to be in 2 significant figures because 0.70 has 2 significant figures in it. And so we are going to round this to 1.5 meters squared. Okay, let's look at the next problem. So 2.4526 meters squared divided by 8.4 meters squared. Okay, the first number has 5 significant figures in it. The second number has 2 significant figures in it. So when we do the math, we need to have 2 significant figures in our answer. So when we do this, we're going to have to round our final answer to 0.29 meters squared. And last problem. Now, 0.365 meters squared divided by 0.0200 meter. This has 3 significant figures in it. This number also has 3 significant figures in it. So our answer needs to be rounded to 3 significant figures. And so we're going to round this answer to 18.3 meters. Okay. That is the conclusion of your Chapter 3, Section 1 video. I know it was long, but thank you for sticking out with it. And remember, all of the information on these Google Slides has been acquired and adapted from Pearson Chemistry's 2012 edition of the textbook resources CD and pearsonchem.com. Thank you.